So I discussed this old paper with Bertram and Leisesfeld. Yeah, we proved the following thing. We say that look at the f naught to fm to be this ideal generated by a bunch of equations, yeah, polynomial, and they satisfy some inequality on the degree that d0 is bigger than d1, bigger than dm, and assuming that this the projective scheme defined by this J is actually a non-singular variety of codimension E. Then the thing that we prove is that the ideal sheaf, not only the ideal sheaf, but you can also prove it for the power of the ideal sheaf, satisfies some regularity bound. And again, it failed to be regular. If the bound cannot be improved by one, then the boundary case is precisely the complete intersections. And now, we left out a very obvious question we didn't answer. Now you have this ideal J generated by F0 to Fm, and it is contained in the homogeneous ideal I of X. And because the scheme is smooth in the projective space, these two ideal J and Ix is only differ at the origin in CR plus 1. And so therefore the quotient is something of finite length, and that just simply means that for high enough degree t, that Ix of t is equal to J of t. The degree t part will be matched for sufficiently high t, and we define the saturated degree of J to be the minimum t naught, such that J of t equal to Ix of t for all t bigger equal to t naught. And now, more generally, for a homogeneous ideal J, the saturation is defined by basically some sort of colon ideal. I mean, here it's just look at all the element F in S, such that the F, when you apply M to K, then it will annihilate the element in S small j. And this is the saturation. Yeah. So our theorem with Haar and isocell is the following. Basically, we give a bound on the saturation degree. And the saturation degree in this setting is that this saturation degree is bounded by d0 plus d1 up to plus dr minus r. And more generally, if you have if you look at j to the a, the saturation degree of j to the a is equal to less than equal to a times d0 plus d1 plus dr minus r. Now, this question is also related to symbolic power of the homogeneous ideal corresponding smooth variety also. I mean, there's some written commutative algebra comparing the symbolic power to the regular power. And I think together with Leisesfeld and Karen Smith, we're using multiply ideal and asymptotic multiply ideal, things like that. We first obtain some non-trivial bound, and then this would improve by Hochster and Craig Unicki to singular situation and positive characteristics. And anyway, for here, remember the symbolic power ideal is just simply this polynomial f in S, as the order of f is bigger equal to a for a general point x in X. And clearly the regular power is sitting inside the symbolic power. But one wants to understand how to compare them. Basically, in the case X is smooth, the Ix is only different by the saturation essentially is just the symbolic power. And then what you find is that the bound for the saturation degree is also given bound like this. So, okay. And the next theorem is just about reduced curve. And in this case, that one can, assuming that, again, the philosophy is that Casanova-Mumford regularity control complexity in a lot of computational problem here. So if you know that the ideal is M regular, then again, you can control the saturated degree. In this case, the saturated degree is bounded by A times M. And in fact, this bound is sharp. For instance, I check it for rational normal curve. Okay. the key ingredient of proof of theorem 2 is the so-called the Eisenberg Buchsbaum-Eisenberg complex. In the situation very similar to like many other things, like the and we can compare that with the surge power of E, but when you're doing the twisting and push down, yeah. And then you can check easily push twisted by O of A and push down. You get the exactly the Eisenberg, the Buchsbaum-Eisenberg complex. And of course, dimension E, we have this blow up, and E is the exceptional divisor. Then I need to understand the push forward of O of E from O of A, E from upstairs to downstairs, and I want to understand the direct image and higher direct image of these things. Now, if A is negative, then minus A, so you have something O minus AE, then it's well known that the push forward for O minus AE when A is positive is just the ideal shift to the A power, and the higher direct image is equal to 0. Now, what happened when the power A, you have O of AE, where A is positive instead of minus A, you have plus A, then what happened? Well, for degree 0, then we just push down to the structure sheet. And for the high direct image, you want to check that between the fiber is P of E minus 1. Basically, you can see by, for instance, the formal function theorem that between 1 and J minus 1, this thing all equal to E minus 2, this thing all is equal to 0. But you would see contribution from the high direct image for the RE minus 1 mu lower star or AE. And the assertion is that this thing is equal to some X group downstairs. Okay. Now, so we need to prove that the xi of ci is equal to 0, and this in turn reduced to vanishing of the bundle of the form x sk of n tends to determinant of n tends to O of L for L bigger than minus R. So we just reduce to this calculation about symmetric product of normal bundle and the determinant of the normal bundle. Okay. Now, for the case of the theorem 4, remember that is about the knowing the regularity of a reduced curve, and we want to compute its saturation degree. That is what theorem 4 is about. And this involves another trick that is somewhat similar to the trick that used by Gruson, Leistensfeld, Paskin in the regularity of the curve. Now, so in general, if you have a smooth variety and you have X inside M, and suppose you have a complex resolving the IX, so you have something like this, then Weismann proved that there is something called the Weismann complex, resolve the power of the ideal. Now, you remember X here is not something defined by regular sequence, so one does not expect to be something really nice, yeah. And so, but there, nevertheless, there's this Weismann complex, and this is how you construct that. This is the first few steps of the complex. Now, remember, I'm not asserting the complex is exact. In fact, complex often is not exact. The first few map are the first map from SA of U0 to IX of A is the obvious map, yeah, and also the other one. And these are the first few that are just the obvious map. And so, in general, the case that the complex you set CK of UJ is if J is even, is a symmetric product of UJ. If J is odd, then you define the exterior product, and then the I piece of the complex of the Weismann complex is just this direct sum over these graded pieces of this type. And for us, it's not so important really, except we just need to know that in our case, we can resolve the complex because we know M regular. So you can say that the first step is, this looks like sum of O minus N, and the next step is of the form of sum of O minus N minus 1. So we can bound the regularity of the Li and from the description. And if X is non-singular, using the essentially, for instance, you can think of just like we know the resolution, minimal resolution in that case from the box-bound isobar complex, though it's not so hard to prove that this statement, this complex is exact.